In this video, I will be observing the effects of surface roughness on wettability and contact angle hysteresis. Wettability is known as the tendency of a liquid to spread on a solid surface and is commonly measured by the apparent contact angle. The apparent contact angle is the angle formed between the liquid vapor and liquid-solid interfaces on a non-ideal surface. In general, a surface is considered wetting when the contact angle is less than 90 degrees and non-wetting when greater than 90 degrees. Apparent contact angle measurements are usually inconsistent as the values are dependent on surface contaminations and the methods of measurement used. Contact angle hysteresis is quantified as a difference in the maximum contact angle, called the advancing contact angle, and the minimum contact angle, called the receding contact angle. For hydrophobic surfaces, low hysteresis is desired because the droplet would have an easier time rolling off the surface. In this video, I will be using the tilted plate method to measure the advancing and receding contact angles right before the droplet starts to slip. The effects of surface roughness are usually described using two states, the Wenzel state or the Cassie state. A droplet is in the Wenzel state when the liquid penetrates the cracks on the surface and applies more generally to wetting systems. In the Cassie state, an air-liquid interface is formed under the liquid and is more applicable to non-wetting systems. In this experiment, I will be observing the effects of surface roughness on wettability and contact angle hysteresis. I will be altering the surface of foam plates with 3 different grades of sandpaper and using water as my liquid. For my experimental prediction, I anticipate that hysteresis will decrease with increasing roughness because the surface will become more hydrophobic, which will decrease the difference between the advancing and receding contact angles. In order to achieve an even roughness on the surfaces, I placed the foam plate strip on a flat surface with a double-sided tape and sanded in a circular motion for 3 seconds, rotated the strip a quarter turn, and sanded again, and repeated this process until the surface was evenly modified. I also tried my best to remove any dust from the foam plate surface. This is my tilted plate apparatus. It's just a protractor with a piece of styrofoam supported by a nail hinge. I stuck a needle at the end to keep track of the tilting angle, and I also tried to make sure it was evenly leveled. And for my setup, I attached the foam plates to the styrofoam platform with a double-sided tape. For each experiment, I used a total of 3 drops and colored my water with food coloring to help visualize the droplet. Right after placing the droplet, I gradually tilted the droplet on the surface. The same procedures were done for all samples. To observe the effects of surface roughness on wettability, I measured the initial contact angles of all samples using ImageJ software and took the average of both sides. Without surface treatment, we see that the droplet is wide, and as we increase surface roughness, the droplet gets more spherical. In particular, for the 100 grit sample, it looks wider because the droplet itself was an odd shape. I looked at it from the top view after dispensing it, and it had an indent on its right side, probably because I did not drop it properly. I accidentally stuck the droplet to the foam plate while dispensing. I also used ImageJ to measure the advancing and receding contact angles. These are adjusted images of the droplets right before slipping. From a first glance, it looks like the 60 grit sample exhibits the lowest hysteresis. This is a table summary of my results. Under Wenzel analysis, it was expected that the increasing roughness would make the initially wetting surface more wetted. However, instead, the surface became non-wetting as a result of the roughness size being too large for Wenzel analysis to apply. Beta is the tilting angle right before the droplet started to slip. We can see that the tilting angle and the hysteresis are in agreement, where the highest hysteresis sample was able to withstand the greatest effects of gravity. I speculate that the 220 grit sample exhibited the most hysteresis, as it provided the most optimum groove height for the 3-phase contact line to pin down and counter the gravitational force. In contrast, I think the groove height provided by the 60 grit sample was too large for the 3-phase contact line to supply much support. Finally, I am very surprised that the untreated surface exhibited the lowest hysteresis, as it is the most wetting. Looking back to the advancing and receding contact angles, it just looks like the 60 grit sample should have the lowest hysteresis. Perhaps my surface modifications were uneven or my contact angle measurements were inaccurate.